Hi, my name is Jake Venzel, and today I'm going to be walking you through my major assignment B presentation, in which I analyze the heat transfer rate of PC water cooling. So there's two types of major cooling that you can implement in a PC. The first one is air cooling, where the pros are that it's cost effective, it's the safest way to cool a computer, and it's super easy to install. Its cons are that it's loud, it takes up more space than other methods, and that it doesn't offer peak performance that those other methods offer. And it's comprised of three main components. The first one being the heatsink, heat pipes, and then lastly the fan, which as you can see in this picture over here to the right. The second major form of cooling for PCs is water cooling. The pros of this are that it's quiet, it's great for overclocking, and it has the best heat regulation out of the two that we're talking about today. Its cons are that it's more expensive than air cooling due to it being more complicated, leading it to being prone to leakage and also having a more complicated installation. And it's comprised of six main parts. Uh, the first one's the radiator, second's the pump, third one's the connective tubing, fourth one is the cold plates that connect to the processor and the CPU, and the fifth one is the fan, and the sixth is the reservoir. So as you can see here, this is an example of a pump that I have in my personal computer. It's it's a pretty small pump, but its flow rate ends up being a 0.125 GPM. Its dimensions, as you can see, are smaller than you would normally think a pump would be in a computer. Its mass is 135 grams. Its power output is 10 watts. Its voltage is 12 volts and its amperage is zero point 0.6 amps. And it has two different sets of tube diameters that you can interchange throughout. These two different tubes came with the pump itself. And those two diameters are 0.013 meters and 0.025 meters. So the overall objective of my experimentation was to see what size tubing allows for the best heat transfer rate of the water in the water-cooled PC. So my equations used for this experiment were the velocity equation, which then I used to plug into the Reynolds number. I then found out if the Reynolds number was laminar or turbulent, and then I used the relationship with the Nusselt number to solve for the H. And then I plugged that H value into the rate of heat transfer equation, as you can see on the bottom. So for the first run through the experiment, everything was held constant as to the programs that I was running in the background. I was playing the same level of the same game um, at the same amount of time for each run. So it should basically come out to close to as constant of values as I could possibly get. So the diameter for my starting one was 0.013 meters. And then I managed to get all the values, as you can see down below, that are associated with water. And the temperature out and the temperature in are the water is supposed to be at room temperature, and then the T out is the overall temperature of the computer as it's undergoing the stresses of playing the game. So I plugged those values into my Reynolds number, and I got a number of 866.49, which is a laminar value. I then found that the Nusselt number is equal to 3.66 due to the fact that the pump is undergoing a continuous flow through uh, tubing, and that allowed me to equate the 3.66 Nusselt number to the HD over K, which I plugged in my diameter over my K value, and I solved for my H, which gave me a value of 168.92. I then plugged my H value into my rate of heat transfer equation, which gave me a rate of heat transfer of 0.782 watts. I then did the exact same thing on the next run, but with a different diameter running at all of the same constants as I said previously. The diameter was changed to 0.025, and everything else held constant, including the temperature that it was running at as well. So once we plugged all those in, we can see that we got a Reynolds number of 1666.33. We then got a Nusselt number of 3.66 due to the fact that the Reynolds number is laminar. And this led us to get a H value of 87.84, which then gave us a rate of heat transfer value of 0.409 watts. So in conclusion, as you can see, with everything else held constant throughout the computing process, except for the diameter, which increased from 0.013 to 0.025 for two different runs, this caused an increase in the Reynolds number overall and a decrease in our H value, which then caused a decrease in our rate of heat transfer. And we can conclude from this data that because the rate of heat transfer decreased, it's showing that as the tubes increased, the amount of heat that the water cooler is taking off of the components is being reduced. And this is not good for the component because it's being put under a lot of stress trying to play a very demanding program. And if it doesn't have the correct cooling, then that can end up destroying your components. So even though the thought of increasing the tubing size in a computer, which a lot of beginner computer builders do, might seem like a good idea, if you don't have a powerful enough pump, your computer components will suffer and overheat and possibly get fried due to that pump not being powerful enough and not enough cooling being pushed through the system itself.